So hello dear students, today I'm going to discuss a very important and a curious topic in the field of quantum mechanics, which actually refers to what quantum mechanics actually means. So what is the meaning of the theory of quantum mechanics? So it was first of all pointed out by Einstein that the quantum mechanical theory is in somewhat way incomplete, and he gave rise to a paradox known as the EPR paradox. And according to him, the paradox was such that somehow the theory of quantum mechanics was incomplete and was not able to give the real meaning or the reality, what is behind the theory and what is actually, you can say, the philosophical understanding behind the theory is lacking. So there is something here, something incomplete in the theory which has to be added so that the theory becomes more philosophically sound. So it was a paradox which was raised by EPR, that is Einstein, Podolsky and Rosen, in their paper in 1935, and it raised a lot of very basic and fundamental questions about the meaning of quantum mechanics. And then later on, John Bell uh, gave rise to, he produced in his work, in his paper, a set of inequalities, and with which he was able to end the question that was raised by Einstein about the hidden variable theories. That is, if there is some hidden variables are there which are present, which would make the quantum mechanics complete. So according to the work done by Bell, it was proved that there can never be any local hidden variable theory which would be able to make quantum mechanics complete. And quantum mechanics as such, whatever it is, whatever the theory is, it is as such, whatever, you have to take it with a pinch of salt or whatever. But since it is there and it's predicting the right results, that's the only thing that can occur. And if you talk about some deeper or hidden meaning behind the theory, then you have to go to different kind of understanding about it. And at least for practical purposes, it is correct, and there is nothing hidden behind that theory, and no hidden variable theory would be able to describe the or resolve the kind of paradoxes which arise because of the uh, philosophical inconsistencies. So we will discuss about all those things here in the this lecture. So you can see the table of contents. First of all, we will talk about the historical context in the motivation, and we will then talk about the Einstein, Podolsky, and Rosen paradox, and we will try to understand the full mathematical formalism of this particular theory or this particular paradox. And then we will talk about what local realism means and what is the hidden variable theories which are possible under this pretext of EPR paradox. So in this case, we will talk about what are the possibilities of the hidden variable theories, or what are the nature of the hidden variable theories that are possible. And then we will discuss about Bell's theorem and the master derivation of the Bell's theorem, and we will discuss how any kind of local hidden variable theory is unable to resolve the philosophical problems that were raised by Einstein. And then later on, we will discuss some CH-SH inequalities, which are refinements of the Bell's theorem or the Bell's inequalities. And then we will talk about the experimental predictions, quantum mechanical predictions, and how they violate the Bell's inequalities. So the Bell's inequalities tell us that if there is some hidden variable theory is possible, then it has to conquer or follow a certain inequality. So if that inequality is not satisfied, then the possibility of a hidden variable theory is null and void. But then experimentally it was found what quantum mechanics was predicting. Experimentally also the same predictions were found, and what the Bell's inequality in on the other hand predicted were violated with the experimental findings and the quantum mechanical predictions. resulting in the proof that hidden variable theories, at least the local kind of hidden variable theories, are impossible in the context of quantum mechanics, and we have to take quantum mechanics as it is, the way it is, and we have to really actually think a little more deeper about the kind of measurements processes that are taking place and the physics behind the measurement process and all that. So that kind of things were then dealt with by the later physicists, and people are still discussing all those things about the real meaning of quantum mechanics, what quantum measurement means, how a measurement can actually change the system or the wave function or the property of a system. And of course, the original argument of Einstein, which is always, it still remains that the quantum mechanics is not a complete theory. The wave function of the quantum mechanics does not describe everything completely. It's like what Einstein said, that we know completely about a theory, but we don't know about the parts of that theory. The individual parts of the theory are not um, uh, uh, they are not apparent to us, or they don't appear in front of us in a crystal clear manner. Although quantum mechanics claims that the wave function describes the system completely, but the parts of the system are not clearly apparent to us in any kind of a quantum mechanical system. So these kind of things, so that original objection still remains, but the Bell's inequality generally, the experimental confirmation of the violation of Bell's inequality tell us that the contention Einstein made about the hidden variable theories, at least the local kind, so that's are not possible in the case of quantum mechanics. And then we will talk about some experimental things that were done, like the experimental loopholes and resolutions and the other modern developments and applications which are possible in this kind of a case. And then in the end, we will talk about some complete derivation of some of the theorems that we will actually discuss in this particular, you can say, lecture. So this, all these things are going to be divided into a set of lectures, not just single lecture. So there'll be separate videos for. So in the first video itself, we are only going to discuss about the historical context, Einstein-Podolsky-Rosen paradox, and the meaning of local realism and hidden variable theories. So the first three things will be covered in the first lecture. Then the Bell's inequality and the CH-SH inequality and the refinements and the quantum mechanical predictions would be dealt with in the next lecture. And then we will talk about the modern developments, and of course the Nobel Prize that one got, the three people got for the experimental confirmation of the violation of Bell's inequality. So they recently got 4 or 5 years back. So that Nobel Prize discovery about the experimental loop, how the experimental loopholes were covered up and resolved, and more developed and more refined experiments were conducted, which conclusively proved that the hidden variable theory or the Bell's theorem or the Bell's inequalities are consistently violated by the quantum mechanics. So we will talk about all these things in the coming 3 lectures. So now we will first of all talk about the historical context and the motivation behind all of this. So in 1935, Einstein, Podolsky and Rosen, they published a groundbreaking paper, and it was about the questioning, they questioned the completeness of quantum mechanics rather, and their central claim was that quantum mechanics is incomplete, and uh, it has got some element which is hidden and some element which would actually expose the actual physical reality behind any kind of a physical system, which is not completely described by the wave function. And uh, it is actually, we are going to discuss this famous quote in Einstein about the real factual situation of the system S2 is independent of what is done with the system S1, which is spatially separated from the former. So this kind of why what happens for two systems which are separated far apart, they are able to affect each other according to quantum mechanics faster than the speed of light. They can affect two systems, two separate, spatially separated particles. They are able to affect each other uh, at a very large distance, and in fact, almost instantaneously. So that is something which was not acceptable to Einstein. So he proposed a paradox. So he proposed a thought experiment, and in that thought experiment, he tried to create a paradox and logically prove the inconsistency of the quantum mechanics. And it was based upon the principle of local realism. And what local realism means. So there are two terms here. One is local and the other is realism. So what realism means, that let us say if we have a system and of a different number, a set of particles, and each particle is going to have a certain property associated with it. So the property of that system, or the collection of particles, the different properties, they exist without the interference of observer. So they are observer independent. Rather, that is what is meant by reality. That is, and let us say if you have a system and it has got each particle has got some velocity, it has got some mass, it has got some energy, it has got some position, it's got some angular momentum. So all these things are existing despite of the observer. They are not observer dependent. That's the reality. The system or the physical world is separated from the observer, and the observer is only just trying to measure or these properties with the least amount of interference. And the second thing is about locality, and the locality means that no influence can propagate faster than light. So that means if there are two objects which are separated very far apart, and if one object is able to affect the other object in certain way, it can only do by some causal connection, and that causal effect is basically propagating with the speed of light or less than the speed of light. It cannot propagate faster than the speed of light. So the speed of light is the fastest limit, and it cannot go beyond any kind of an effect which is being which is actually been felt at a distance. That effect has to be felt uh, after a certain time, and that time span is such that the process of conveying that effect from the cause to the observer, or the effect from the cause to the effect, that would take that the speed of this conveyance would be less than or equal to the speed of light. It cannot be greater than the speed of light. So this EPR paradox actually is a proof by contradiction. So if they say that we assume that these two conditions are held by any physical system or the physical world, that is, local realism is a condition which has to be held, or which has to be you can say, one can say that it is a system inherent in any physical world, and we cannot get away with this kind of a thing. So that has to be there. Then by contradiction, one can prove that quantum mechanics is inconsistent, because it actually violates the local realism in some way or the other. That we will discuss, or we will describe in the coming slides. So actually here he says either quantum mechanics is incomplete. So he is not actually saying that quantum mechanics is wrong. He's only proposing that quantum mechanics is incomplete or locality is violated. So either you have to give away with the concept or the precept of local realism, which is a philosophical construct, but at the same time which is applicable to any physical world. But either you have to if you have to violate the locality, either, or somehow quantum mechanics is incomplete, and there are certain hidden variables or certain extra variables are needed, which will make that theory complete. And later on we can work on those, and we can find those variables, and from there we can actually ascertain that the locality is not violated. So how Bohr, the famous Niels Bohr, who was the father of quantum mechanics, and when this paradox was raised to Bohr, in front of Bohr, so he did not accept the paradox. So how he actually responded it, that he said that if you are talking about any measurement that you are doing, and according to the EPR paradox, if somebody tells you that two simultaneous variables which are canonically conjugate, like position and momentum in case of quantum mechanics, so they cannot have any simultaneous values together at the same time. So position and momentum are conjugate variables in quantum mechanics. They can never have, according to the Heisenberg's uncertainty principle, they can not simultaneously have fixed values. So in that case, he said that any experiment, basically reality according to him is context dependent. So he says that reality is dependent upon the kind of measurement we are doing. If we are measuring the let's say the position, then the position is the reality, and if you're measuring the momentum, then the momentum becomes the reality. So any kind of physical reality is context dependent. And he invoked the complementarity, that is simultaneously assigning values, definite values to complementary variables like position and momentum. That is not possible in quantum mechanics. So the whole question of completeness, he argued, is ill-posed. But the debate remained open there after a very long time. So in 1964, rather, it was John Bell who conclusively ended the debate by proposing about the impossibility of any local hidden variable theory in quantum mechanics. So let us just now, today, and this time we are talking about the Einstein-Podolsky-Rosen paradox. So we are going to talk about the full mathematical description or the framework of this particular paradox. So let us start with the original two-particle system. So let us say we have two particles, uh, and these two particles are in a correlated quantum state. So let us talk about the wave function psi here. So here you can see that we have a two-particle state. We have particle 1 and particle 2. Okay, and particle 1 is in the state, these two particles are in the correlated or entangled state, you can say. So basically they are given by this wave function psi, and it tells us that the particle 1, if let's say it's moving with some momentum, let us say minus p in the left side, then particle 2 is traveling with momentum plus p. Okay, so it's like this, that particle 1 and particle 2 can have any momentum, but their momentums are correlated. If particle 1 is having momentum minus p, then particle 2 is going to have momentum plus p, so that the total momentum is 0. So basically it's a correlated state, and it's an integral over all the momentums decay, and P1 is K and P2 is minus K, but it's a correlated state. So if actually a measurement is made, and if particle P1 is found in K state, or it's found in with a momentum plus K, then particle 2 is automatically confirmed to be in the minus K state. That is, the momentum of the particle 2 is going to be in the opposite direction, so that the net momentum remains 0. So we have created two particles, let us say a particle-antiparticle pair, in an experiment like, for example, a pion decays into an electron plus a positron. So in that case, and these electron and the positron, they are flying off in opposite direction, and since the initial momentum of the pion is 0, then the total momentum of the electron and the positron is also going to be 0. Although at any instant, if we measure the momentum of electron, it can take any value, possible value, but once we have actually measured the value of momentum of an electron, we can be sure that the momentum of the positron, which is the particle which is moving in the opposite direction, will have a momentum which would be exactly the negative of the momentum of the electron, so that the sum of the momentum of the two particles would be zero. And so that's how it happens. So this is how an EPR correlated state is described here. So all the momentums are possible from minus infinity plus infinity, but according to this correlated wave function, if P1 is equal to K, the momentum of particle 1 is K, then P2 has to be minus K. Okay? And then you can look at these physical interpretations. Particle 1 and 2 are spatially separated. They are far apart from each other, of course. The momentum of particle 1 is measured, which is P1, which is equal to K. And the particle 2's momentum is perfectly determined by, once we measure the particle 1's momentum, and it is perfectly going to be equal to minus K, but no interaction occurs between the particles. So the two particles are very far apart, but the moment I measure one particle's momentum, instantaneously I'm sure that the other particle's momentum is minus K, if the first particle's momentum is plus K. So this is basically a correlated system, in a momentum correlated system. So let us say we talk about the EPR's criteria for physical reality. So the definition is EPR's physical reality criterion, that if without any way in disturbing the system, we can predict with certainty the value of that physical quantity, then there exists an element of physical reality corresponding to that quantity. So what he means is, or what the EPR mean is, that if there is a system or a particle, and we can predict with certainty what it, so the property of that particle would be, like for example the property can be momentum or spin or angular momentum or energy or whatever. So if we can predict it with certainty, then that particle must possess that property. That's the physical reality. That is, if we can predict it, then it must have the same property, and that is the physical reality. That's called the element of physical reality corresponding to that quantity. So that quantity is physically real. There is an element of physical reality behind that quantity's property, and that exists. Now, accordingly, if we talk about a mathematical statement in quantum mechanics, so some observable Q, which is defined by the operator capital Q, and its eigenstate is Q. So this is Q is the operator, and this is the eigenstate, and the eigenvalue is Q. So it's like that if Q operator operates on the eigenstate Q, then it produces the same eigenstate Q with an eigenvalue Q. Okay, so this is the eigenvalue equation that this is going to follow. And so let us say after the measurement, if a state psi of the second particle evolves to the eigenstate Q after particle 1's measurement has been done, which is with proper probability 1. So the particle 1's measurement has been done with probability 1, and then the eigenstate of the second particle, let us say, or the combined eigenstate evolves to an eigenstate Q after the measurement, then Q has the real value Q for particle Q. That means the operator Q or the observable Q, its value when one would observe would be definitely Q for particle Q prior to any measurements on particle 2. So even if we don't measure anything on particle 2, we are confirmed that the particle 2 is going to have this value small q for the observable capital Q. Okay. So then Einstein and Podolsky and Rosen, they gave this incompleteness argument. So what they said, that if we assume all the things that we have said and we are having this wave function, it is perfectly correlated, and the two particles expectation values of momentum are correlated with each other, and then from these assumptions and from the logical argument, one can actually come up with an inconsistency in the quantum mechanical theory. So these are the three assumptions. The first assumption of the incompleteness argument is that physical quantities have definite values prior to measurement. Okay, so that is the reality. That's the reality argument, very important. According to Einstein, any physical quantity would have a definite value prior to measurement. Then the locality argument is there, that the measurement of spatially separated systems are causally independent. That is, it's like that if the particles are spatially separated far apart, so they are unreachable to each other, then whatever is happening to one particle is not going to affect the other particle. So they are causally independent of each other. So they don't affect each other. The causality condition is such that one particle cannot cause anything or any effect on the other particle. And then quantum completeness. This is another assumption. And according to it, the wave function psi is complete, that it completely describes the system. And whatever we want to know, whatever information we want to get of the system is going to be obtained from this wave function. So according to Einstein, Podolsky and Rosen, these three statements are mutually inconsistent. So let us see how it happens. So the sketch of the proof is simple. Let us say particle 1's measurement determines particles 2 state with certainty. So by correlation, according to the quantum mechanical correlation or the wave function, if we measure particle 1's, then the particle 2 state would also be determined with certainty because of the correlation that is existing between the two. That is, the wave function is correlated or entangled. The determinism occurs instantaneously across space. So the assumption B is followed that this is basically the determination occurs very much instantaneously. So it's like the locality is violated. Whatever determination is there, it is actually transferring from one point to another instantaneously. So that means particle 2 must possess definite value before its measurement. So that means if instantaneously the other particle is having that particular value, and which is not causally created by the particle 1. So the particle 2 is having that value at the time of measurement at particle 1, then according to assumption 1, particle 2 must possess definite value before the measurement. So the particle 2 must have that value even before the measurement. Then according to quantum mechanics, particle 2 is actually in a superposition state. It's in a correlated state, but it's an entangled state with all the possible momentums are there. So the entangled state that we talked about, the psi that we showed in the earlier slide, it had all the possible momentums from minus infinity to plus infinity. So quantum mechanics tells us that particle 2 is actually in a superposition state with all possible momentums, and the value of momentum is not definite. Thus, the wave function is incomplete. It omits hidden variables because contradiction with the C assumption that we have, as we go back, we can see quantum completeness, the wave function is complete. So accordingly, if some object is in the superposition state, but it is not actually having a reality behind it, which was claimed by Einstein, that is, either the reality is not there or the wave function is incomplete. So there is a logical inconsistency. Okay, so if the particle 2 is not definitely having a value before the measurement, that means assumption A is violated, or wave function is incomplete, that means assumption C is violated. So at least one of the assumptions A, B or C must be abandoned. Okay, and what about B assumption? The B assumption is locality. Either one can also say that it has the message has passed instantaneously. So from particle 1 to particle 2. So all these arguments tell us that either A is wrong or B is wrong or C is wrong. So this is how any one of the three has to be abandoned. But then all the three are basically valid philosophical or logical constructs in a physical universe. So if you have to abandon out of the three, Einstein chose C has to be abandoned. That is, the wave function is incomplete. According to Einstein, his choice was that C has to be abandoned and the wave function has to be incomplete, and there are some hidden variables which would be revealed later on when further delve into the study of quantum mechanics. And then later on it would be found that the quantum mechanics has a certain other variables associated with it which would not be which are not there right now, and which makes the quantum mechanics incomplete. So after that, by people like Bohm and Schrodinger, etc., they started the hidden variable program, mainly Bohm. So what happened was physicists started exploring whether local hidden variable theories could restore determinism and locality while reproducing quantum mechanical predictions. So all the three conditions may not be violated, but the C condition may be violated, but the A and B condition may not be violated, but the C condition tells us that there must be hidden variables. So people started looking for those hidden variables. So a hidden variable program was proposed. So there was a theory postulating that each quantum system possesses an additional specific variable lambda, which is called the hidden variable. And then the complete state of the system is given by psi and lambda, which is the wave function and the hidden variable. Then addition of this hidden variable lambda to the system completes the state of the system. Then all measurement outcomes are deterministically determined by psi and lambda and the measurement settings. So then after introducing the hidden variable, all measurement outcomes are deterministically verified or determined by these two variables and by the measurements that we conduct on those systems. Then what about the quantum statistics or the averaging or the, you can say, the indeterminacy in quantum mechanics? They arise from averaging over the ensemble of lambda. So lambda itself is one variable, but it can take several values. A variable can always take several values. So once we average over all the values of lambda, the quantum statistics would arise from there, from the averaging process of the hidden variable over the ensemble of all the values possible for lambda. And the fourth and the most important is the measurement on system 1, subsystem 1, is independent of the measurement settings of some system 2. Okay, so subsystem 2 and subsystem 1, whatever measurements we do, and if they are separated causally with respect to each other, then the measurements on first system and on the other system, they are going to be completely independent of each other, and that's the Bell's locality argument. And according to this Bell's locality, then he derived a condition for those quantities that one measures after after including all of these conditions, and he found out an inequality between the different variables or between the different probabilities of measurement, and then he found that those inequalities are going to be violated if we actually take quantum measurements to be correct. Rather, the quantum measurements which are also experimentally verified, those quantum measurements which are theoretically predicted and experimentally verified, so they are actually violating those inequalities which arose when we include a local hidden variable in the quantum mechanical framework.